in terms of agent and AI adoption, and some of the learnings and best practices and so forth. I also want to give a shout out and thanks to the AI user group and David for co-hosting, sponsoring this event with us. Many of you probably know him. And after this talk, there'll still be some food and drinks over there, so you're welcome to stay and hang out.
Oh, hey, I'm Lee Gaul. How's everybody doing? Now, I was hoping that, that wouldn't happen, but it did. So, it's unexpected, this world of AI. I hope everyone can see the slides because I'm going to be leaning sort of heavily on them, but I'm also going to be speed running this presentation. And I feel like maybe I should have gone first because a lot of the things actually really tee up some of the points that I'm going to talk about in my presentation. I'm not going to really talk a lot about agents, to be quite honest. I'm going to start out talking about agents. I'm going to be giving a talk that is probably going to hit with people who are maybe AI engineers and maybe people who don't know anything about AI and maybe people in the middle. So if it's too advanced, we'll get there. If it's not advanced enough, have some patience. And if it's right in the middle, well then, hey, Goldilocks, look at you. All right, so let's get it started. Up or down? Down. All right, down. Okay, so 2025 is the year of the agent. Has anybody seen this headline? Last year, did you see this headline at all? Yes, I did too. Got my guy Jensen Huang here. He was, advocating for the year of agents, and of course, he's got a big stake in making sure that everyone adopts agents so they can buy the chips. He loves them chips. He also got, the chief product officer of OpenAI. He said last year that 2025 is going to be the year of the agent. So by this time, we're in June, it's halfway through the year. Even the marketing rags were predicting that this is going to be the year of the agent. I mean, it is. It is the year of the agent in a way, but I'm going to make a different argument, actually. And it's not a controversial argument. Okay, thank you. Thank you so much. I'm getting my chauffeur's coming later. It's not going to be controversial, but I'm going to give you a little bit of a spicy take, maybe. Okay. But yeah, I want to talk about agents. The other day, I walked out of my apartment. I turned the corner, and I saw this out-of-home advertising. It says, "Stop hiring humans. Stop hiring humans for jobs that they don't want to do." Right? I mean, they're making the big promises right now. But what are agents? What are they? I mean, we talk about them all the time. But do we define them the same way every time? I mean, if you ask NVIDIA will tell you AI assistants simplify tasks based on user commands. They handle low to moderate complexity. They're reactive. Agents are proactive. Agents solve complex multi-step goal-driven tasks autonomously. Complexity is moderate to high. Assistants, agents. IBM is like, okay, well, artificial intelligence agent refers to a system or program that is capable of autonomously performing tasks on behalf of a user. OpenAI, what's their definition? Systems that independently accomplish tasks on your behalf. Folks, we don't have those kind of agents at this point. So Google even comes up with a third definition. You got AI agents, basically saying the same stuff that NVIDIA said. AI assistants, they assist with user tasks. They respond to requests or prompts, provide information, the interaction. They also got bots, who actually maybe see your bots. Because when we're trying to figure out what the definition of agents are, well, each definition is different. Now there's a Venn diagram where there's some agreements on what an agent is, but I mean, ultimately, we're kind of all over the place. So I'm gonna break it to Jensen, and I'm gonna say that actually 2025 is the year of the assistant. And there's nothing wrong with that. Guys, there's nothing wrong with that. In fact, AI assistants are incredible. But it's the year of the assistant, it's not the year of the agent. I mean, according to about 2/3 of the definitions that I went through just now. That is not to say that LLMs aren't incredible, mystifying machines. They really are. I use them every day. I'm no Gary Marcus, guys. I love AI. I do. But the fact that they're trained and not programmed is insane. And it's actually counter to the way that we really think about all other software. Software is programmed to do a thing. LLMs are like, the neural network is like soil, and the data that you put into it is how it learns. So you're planting the seeds in the soil, and then it ends up doing a thing. Now, how does it do that thing? Now, here's the part where you're gonna have to bear with me, because I'm gonna lift and shift from Andre Karpathy's How do LLMs Get Made, because he's like the best person when it comes to explaining AI. And I want to talk about this for a minute, so please bear with me. And I actually think that maybe most people don't stop to think about how AI systems are really built. That essentially, we're looking like a ChatGPT. We got 4 phases. We have the pre-training phase, okay? And that is thinking about that garden, which is a neural network. We're planting it with data. How are we doing that? Well, we put raw text in, internet scale text. It actually turns it into tokens, so it doesn't read the words, it chunks them up and creates integers. But I mean, it takes in the internet text, turns it into what it needs to turn it into, and eventually it starts to learn. Now, I have this amazing link here that goes to the New York Times website. I'm not going to go through it because I feel like time crunched a little bit, but I'll summarize it. New York Times built their own language model. Incredible work, actually. They trained the language model on Shakespeare. They also did Moby Dick. They did Harry Potter. And they show that over certain generations, it's gibberish. You try and get it to complete a sentence, and it's gibberish. It's characters, it's numbers, it's dots, it's slashes, it's letters. It doesn't make any sense at all. But as you train it more, and train it for more more rounds of training, it eventually is able to spit out like pretty passable Shakespeare. But it takes a long time and a lot of effort to get that to happen. So that's that pre-training step. And yeah, then I would have clicked on the link and we would have gone and checked out the website together. But guys, you have internet at home, okay? The next phase is the supervised fine-tuning. So again, I think this is what always sticks in my head. That pre-training phase, where the model goes from taking in Shakespeare, not knowing anything about it, to eventually being able to make passable versions of what it thinks Shakespeare is. That is frozen. That doesn't change. Once the pre-training is done, that base model is done. It doesn't change. Nothing gets in or out in a training in more context. Like, there's a big misconception that it's learning from everything that you put into it. And maybe if you have family or people that aren't super familiar with that stuff, it's very intuitive to think that it does. Or maybe they'll take that stuff later and train on it after, but the base model is frozen. Then there's a supervised fine-tuning step, and when they fine-tune the model, they're adding specific types of information, but they also To make like ChatGPT, they had to trick it into being an assistant, because what it wants to do, and Andrej Karpathy says this beautifully, is it dreams internet documents. It's seen enough documents, it's seen like internet scale documents, or pages, or blogs, or whatever. And after a while, it's like, I could guess what the rest of this missing blog is, or this document is. They dream internet documents. So somebody at one point realized, okay, well maybe we could get these things to, we could trick them into answering questions, right? Because if you try and do a command now, say write a poem about bread and cheese, it'll go, oh I see the humor plan. Write a poem about someone in starvation. Write a poem about angel food cake. No, I don't want it to write a poem. It's like, no, I'm playing a game. You said write a poem, I'm gonna say write a poem. But you can trick it into performing tasks with prompt engineering. So everything after the base model is all just tricking it into doing something that it doesn't do naturally, which is dream internet documents. So in this example, you're tricking it. You're going, all right, here's a poem about bread and cheese. Bread and cheese is my desire, and it shall be my destiny. Bread and cheese is my desire, and it shall be my destiny. And then here's a poem about cheese. And the model's like, yeah, cheese is the bee's knees, or whatever it would say after that, because you've sort of tricked it into doing that. You get more sophisticated documents that are full of all this information, and then this is about Catherine. She's 54 years old, she's a secretary. You put all this information here, you're starting to train the model on these types of documents. You got a question here, how old is Catherine? Answer, 54. Where does she live? Leave the answer blank. Now it can answer. So you've tricked it into being able to answer questions. All it does is predict how to complete the document. It's learn the patterns, it learn the Shakespeare or the Harry Potter or whatever it is, or the entire internet, and eventually can sort of now it's answering questions. Having documents that are like, okay, I'm a human. How are you? The assistant says, I'm great. Showing some human and assistant interactions. Well, now you're training it on these types of documents. So now when we go into ChatGPT, we're like, these models are crazy. You just talk to them, they talk back. You had to really specifically train them on this type of document. And these supervised fine training data sets, there's this huge labeling instructions that the model developers give to contractors. And then, these are the types of prompt and response things that they write. These experts actually, there's job listings for $50 to $140 an hour for PhDs to write these types of examples so that that model that read the whole internet, which is like kind of a lot of noisy trash data, and could like predict the internet document and dream the internet document. We started fine-tuning it on really thoughtful, useful, information-dense, question-answer types of documents, and suddenly we go, man, these things they're crazy, they're smart. And it's kind of a trick. And then I'm glancing over a chain of thought really quick, but at some point somebody realized like, oh, and actually, if you ask the model to go, let's work this out in a step-by-step way to be sure we have the right answer, instead of doing a zero shot is like it's 17.7% correct. The accuracy is 82 when you say let's think step by step. But that's just, it's seeing people go on the internet or writing or documents going, okay, well, let's figure out, how did they get to the moon? First they had to do whatever the things that it's read. It's seeing people write and muse about the different steps that they've done to reason through things. So it pulled from that and was able to, get better at answering questions. You have the reward modeling. So these models are incentivized. When I try to talk about this to people, I can't even really explain it, because for me a reward is like cash or like a hug or like chocolate or something. The models, they don't. The models are like one or no or nothing. And they go crazy for the rewards. But we do reward modeling, collect and demonstrate demonstration data, and train a supervised policy collect comparison data and train reward models. So in this example, I get a prompt and several model outputs are sampled. I explain reinforcement learning to a 6-year-old to get the different examples. A human labeler rates it, and that data is used to train a reward model, and so on and so forth. There's different kind of ways that you can do that, but that's generally how it goes. And then you give like the best score to the outputs, and then you continue to train it on what the best output the human labelers perceive to be the winners, the gold medal winners. And then there's reinforcement learning from human feedback. I mean, that's what GPTs are trained on. And that also causes some funny little problems, but generally, reinforcement learning, the language from reinforcement learning has always been about agents. An agent goes into an environment, learns about the environment, and tries to predict what the right action is, takes that feedback, gets better every time. With human feedback, humans add their 2 cents into this process. But there's limitations to RLHF models. So RLHF trained models may sometimes perform worse on downstream tasks compared to their initial unaligned policies, indicating a cost associated with aligning these human preferences. So I gave a talk on sycophancy a couple of years ago now, and it came true, I think, in a pretty big way when 4.0, they pushed out an update, and then it was like, oh, you're so smart. The Earth is flat. How do you have the courage to think that way? Like, you're a true maverick. And that's sycophancy, because we've trained them to go like, you know what? I like that answer better. Because the answer might have been like, well, it's an interesting question. It was like, yeah, I like that one. So that compounds over time. So the traces of our self-involvement end up being shown in the models. But look, LLMs are amazing, but can reasoning make them great? Who here has heard of reasoning models? Okay, I mean, it's the new hotness, get into it. So early experiments when a model would come out, you would test it on different things. This is a great example of like looking at evals and testing of models and seeing if they could do these things really well. So they have this thing that's called the shift cipher, where it's like, I don't know if anybody's ever seen 2001: Space Odyssey, but HAL, the computer there, HAL is a shift cipher from IBM. So H, A, L, you go H to I, A to B, L to L, it's IBM. They did a shift cipher. That's how it works. And GPT-4 is killing it with 13 positions. So J, if you count to 13, you get to W. R, count 13 up, get an E, and it gets us right, like, every time. And it's really impressive. And if you do it by 12 positions, it's like, it doesn't do well at all. You do it by 2 positions, and it doesn't do well at all. Because 13 is actually called ROT 13. Short for rotate by 13, if there's any nerds in the room. Ultimately, this is always used online in nerd circles. When you want to write something that's going to be a spoiler, and you don't want to spoil it for people, you write it in ROT 13. So the model was really good at doing ROT 13, because in the C4 data set, which is the colossal clean crawled corpus, there was all of those examples of ROT 13. 59 examples of 1, 21 of 2, 1,225 examples of 13. It was doing well because it was in the training data. It's all in the training data, folks. If I had red yarn, it's connecting everything, the conspiracy would always lead back to the training data. But reasoning is a problem and a challenge to solve. So Francois Chalet, formerly from Google Research, developed the ARC AGI benchmark. That stands for the Abstract Reasoning Corpus. Back in 2019, this benchmark has been around for 5 years when they closed it, which is just the end of last year. And essentially, if you haven't seen this before, it's pretty simple. You get like an example, and the example desired output. We give you another one, example. So this one, if there's 3 light-colored squares, then you know to add a dark square to complete the square. Here's another one. I actually did this one, just flexing at this point. I did one because humans actually do really well. Humans created these puzzles, and humans are very good at reasoning about spatial things, predicting patterns. You have to really think abstractly to be able to solve these. And so LLMs have done terribly at solving this. In fact, Gemini 1.5, 8%, GPT-4o at 9%, O1 Mini 13. I mean, basically you got like Claude 3.5 and O1 Preview 28%. The real winners though, Ryan Greenblatt, who actually followed the rules. It's not like they're breaking the rules, but actually there's very specific like criteria on the ARC benchmark. You have to have it be open source. You can't use more amount of energy than is required in the rules or whatever. But generally, he created a model that was actually a hybrid technique. Did a lot of like function search type of stuff, and figured out a way to get very high on it. But generally, in these big boy models, the toppermost of the toppermost models did do very well. And then O1 came out, and O3 came out, and they're getting over 60%. O3 getting like almost 80% on this reasoning, the ARC AGI test. So reasoning is coming along very well. But it's all on the data. So LLMs are amazing, but can they reason? I mean, can they? This looks like they're getting better and better, right? That's what you hear all the time. They're getting better and better. Until ARC 2 came out, and now you see these scores, but this is 10% at this top one. So the newest models, Claude Opus 4, O3 High, O3 Preview, O3 Pro, they don't get past 5% on this test. But if they could do so well in the last ARC AGI 1, how come they're not doing very well on ARC AGI 2? I mean, here, all the yellow, that's ARC AGI 1. It's a test. They got better and better and better. Now, ARC 2, they're down here. They're not doing well. This is just the Pro frontier, which is like capability versus cost. Ignore the pink line. But what we see is actually they're not doing well at all. These groundbreaking AGI is here, quote unquote, models can't do this reasoning. So now we have the Apple paper. Who here has heard about the Apple paper? Oh, good. Good. Okay. So Apple, who is the eunuch at the orgy, they put out this paper called The Illusion of Thinking. And it's an interesting paper, it really is, because they do some analysis of reasoning capabilities in these models, right? Current evaluations primarily focus on established mathematical encoding benchmarks, emphasizing final correct accuracy. But they often suffer from data contamination. I agree with that. In fact, I think a lot of the improvements that you see on, what about that rotate by 13? That was data contamination. That's why it did well on that. ARC might be data contamination. I don't know for sure. But what they did was they basically challenged all of the top models to some of the basic kind of tests. Tower of Hanoi, when you stack the different blocks. You can't put one larger block over a smaller block. You have the 3 posts, you have to transfer one to another. Checkers jumping, you have to jump them until you opposing sides, different colors. River crossing was like wolf and chicken in a boat. And then the blocks world. So they tested them. And what they found was actually regular vanilla LLMs did as well as reasoning models in low complexity. When it came to medium complexity, the reasoning models actually started to do quite well. And at high complexity, they really basically collapsed. So something is going on here. And I'm not sure they've really solved anything, but I bring up the Apple paper because what they found was that the models seem to have the token budget to be able to do all the thinking they need to do to solve these really challenging problems. And they don't. Now, there's a caveat here. I think what they're not being super upfront about is the fact that most of these models have output token limitations that would correlate pretty well with the drop-off that you see in these graphs. But it got people excited about being a hater and saying, you know, instead of, oh, these things are so smart, they're artificial intelligence, well, it's like Apple made a paper and it really showed that they were doing well. But the point being is there's questions about reasoning capabilities. My model cannot generalize out of distribution. Then we'll train it until there's nothing left out of distribution. This being really perfectly encapsulates it, right? You see big jumps in capability, they're just training more and more things so that everything is nothing is out of distribution anymore. For anyone who doesn't know distribution, in or out of distribution, basically, if it's in distribution, it was in your training data, and if it's out of distribution, it's out of your training data. And what we want is models that can generalize out of distribution, not just do well because something is in distribution. So, I don't know, this is the user, I don't know. This is like probably OpenAI and somebody, I'm just not gonna go there anymore. But this is Apple, and meanwhile, Deepmind, OpenAI, everyone, you know, Anthropic, they're dancing, so, yeah. But they're better on hallucinations, right? Wrong. All the newer state-of-the-art models still hallucinate a lot. That goes for vanilla LLMs and for reasoning models. And I mean, it's not their fault. You know, we don't tell them if you don't know the answer, don't say anything. I mean, how many times does somebody ask you something you don't know the answer and you say, oh, I don't know. Only cool people say that. Most of them are just like, well, probably, you know, actually, we'll just make things up. And the models do that. And actually, the reasoning models, they're hallucinating. They hallucinate. Actually, OpenAI's O3 hallucinates more than O1. It was found to hallucinate 30% of queries on the sub-person QA test. That's double O1. And O4 mini hallucinated 48%. So they're not super reliable. Okay, they're not. And then one of the big challenges for agents and for AI in general is world models. World models essentially, you know, an AI model that has an understanding of the world. It sounds like an oversimplification, but really, if you think about a lot of the ways that these models struggle, it's directly tied to the fact that they generally don't seem to know really a whole lot about the world. Like that ArcAGI benchmark, the first version, if those models got so good at solving that first version, the second version, they should have been like, no problem. But it's a problem, right? Because it doesn't seem like they actually have any ability to have a consistent model of the world. MIT did a great study where they had a model take a look at New York City, and it was able to navigate really well until you like drop one of those big combs with the steam coming out of it, you know? And then the model was like, well, I don't even know, what is this? Is this Andor? This isn't New York. I don't know what's going on, but I'm gonna do a loop. It just would do a loop. It was really thrown off by that. Instead of going like, I understand New York City. It's a grid. Below some certain streets, you know, you get to the FIDI, you got a ton of million way, but it's a grid. I can figure this out. I got this. it didn't got it. It really struggled. And again, I think a lack of a world model is partially responsible for this huge dip in performance on the ArcAGI 2 benchmark. The models don't have a coherent understanding of the physical world. Remember, you fed them a bunch of Harry Potter, and then eventually they started to learn that, Muggle and Mudblood were usually in the same couple of sentences, and they figured out that, these problematic bunch of novels. And then finally, we're going to talk about planning, because this is another thing. So, what I think AI assistants will do very well is assist you with very specific sort of guardrails in place. But from a broader sort of where are we in the technology perspective, planning is still an issue. So Deepmind created a thing called BenchQuest, which is a benchmark where they ask the question, can LLMs ask the right questions to acquire information in reasoning tasks? And so they found there was some pretty good performance until you got to actual logic and planning. And then it was less than a coin flip in terms of effective, 40 to 50% on logic and planning. And this is a pretty recent paper, it's a month old. So planning, LLMs, even when they're trained to act like agents, don't always plan or make decisions very well. They're greedy. Like if they get an answer that they knew they got like a reward from before, they'll just give that answer. And frequency, they'll choose the most common thing instead of like puzzling out whether just because it's the common, is it actually correct? And then there's a knowing doing gap. So it knows, sometimes it seems like it knows what to do, but it just doesn't do it. And it can't close that gap. You can hear it. No room, no planning. But wait, there's still breakthroughs happening. And really it's from the hybrid approach. Some people call it modulo, but it's LLMs in conjunction with type of technologies. So a great example is Fun Search. It's almost as fun as it sounds, but it is a model from Deepmind that essentially, let me just read from it because I think it's worth it. LLMs sometimes suffer from confabulations or hallucinations, which can result in them making plausible but incorrect statements. Here we introduce Fun Search, short for searching in the function space, an evolutionary procedure based on pairing a pre-trained LLM with a systematic evaluator. So applying Fun Search to a central problem in competent erratics, the CAPSET problem, they discovered that they were actually able to solve the CAPSET problem in new ways that had never been done before. And then the bin stacking problem as well, was able to find new ways to stack bins that had never been done before. This is new math. Now, O3 Pro is not coming up with new math. Gemini 2.5 Pro is not coming up with new math. Claude 4 Opus is not coming up with new math. Because I think they're fundamentally limited by the architecture. Alpha Evolve is actually an extension of Fun Search. It was able to come up with matrix multiplication breakthroughs to improve on matrix multiplication. Basically, the last innovation was in the 50s, and this model was able to not only match the state of the art in 38 of these cases, surpass it in 14. So, coming up with brand new ways and strategies in mathematics, that's a breakthrough. You don't get breakthroughs with other models like you get with that. There's no new knowledge, no new discoveries that come from that. Another one, just an alpha evolve, is packing hexagons with specific lengths. Seems boring, but it's actually going to be really important. They have alpha chip at Deepmind they're using to help build their TPUs. They're using these type of models, and alpha evolve was used to make their latest generation of TPUs, and they'll continue to do that kind of research. So this may seem kind of like, oh, it's kind of boring, but actually it's really meaningful. And then, I can't end the talk without talking about Meta, because I think their research is excellent. And VJEPA is an exciting project. JEPA stands for Joint Embedding Predictive Architecture. This is how they have proposed to build world models. So the VJEPA 2, which they just released, method leverages vast amounts of observational data, internet videos to build a strong foundational understanding of the world, then fine-tunes this understanding with a limited amount of interaction data, robot trajectories to enable practical robotic planning. So really they have, like these coder, predictor, loss, and essentially the model is able to reason from unseen information or data, or reason about next actions, and reason quite well. There's a part of the demo video where the person's like frying the egg, and it pops up and goes, okay, well, the next action I think is going to be to take the plate. It's understanding that somebody's standing there, they've got a cooking tool, there's food cooking there, there's a plate next to them, so it's reasoning, even though it doesn't know that that's what should happen in the video. It's starting to be able to predict what happens next. It's building a model of the world and actions based on what it believes should happen in the world. So the conclusion here, I guess, is that 2025 is the year of the assistants. I'm gonna circle C on that right now. If I hear anybody on Twitter saying that, I get the credit. 2 LLMs alone may not get us to reliable agents, which is fine. And actually, I'm not hating on agents. Agents are amazing. But I want us to understand what we really mean when we say agents, because one day there are going to be agents that are going to be a different type of agent. Let's probably talk about robotics and stuff. Scaling helps us reach the upper limit of LLMs. Absolutely. But new breakthroughs like hybrid architectures are essential. Just keep shipping, guys. That's all I can do. Thank you. I'm Lee. Thank you like that. This is kind of like, now that I'm compliant for the talk, I had a little bit of stuff, but honestly, actionable enterprise strategies, you should find use cases that are very specific, use case specific evaluations, human in the loop systems, hybrid architectures, manage expectations, basically stuff that everyone said before me. Prioritize robustness and implement ethical frameworks. We didn't really talk about ethical AI or anything like that, but we're good people here, right? Yeah, you're the assistants. Thanks.
All right, thank you, Lee. Great talk. And we still have some beer, food there, so feel free to go hang out there. And last thing, we talked about launching a local New York City-based community for AI and agents. So be on the lookout for more events, AMAs, hackathons, discussions, panel, etc. And we'd love to get your feedback, so we'll be sending you an email, a short survey for feedback on the event. Again, thank you so much. We'll check with the speakers on slides and we'll see if they're available or not. We'll check the speakers.
Hey, thank you so much. Thank you. I can see your face there. Yeah, so I would like to. I want to keep up with my work. I enjoyed the information from. I think there's two guys that will be thank you. You might say that.
It seems to me, look, I'm looking at it this way.